Desi, the floor is yours.
Yeah. Well, good morning, everyone. I'm glad you made it nice and early. So today I will be talking about how we can use Bayesian experimental design to help causality. Who here is working on causality or has worked on causality in any way? Who here is interested in causality? All right, so good. Great. Okay, so please feel free to interrupt me if you have any questions. Hopefully we should have plenty of time for questions during the talk and after the talk. And here is the quick overview of for the next hour. So yesterday, those of you who attended the tutorials day may remember that I presented kind of this introductory Bayesian experimental design tutorial where we focused on parameter learning, right? So we had a model, and the aim of experimentation was to gather data that was useful for learning parameters in a Bayesian model. Today, we will kind of look at extending BED beyond parameter learning. And specifically, we will see how we can actually devise an infinite number of, utility functions still using sort of these information theoretic principles that we described yesterday. Then we will look at active causal discovery with a quick intro to causality. And I will present a paper from a couple of years ago where we used Bayesian experimental design for differentiable multi-target active causal discovery. So that was ICML 2023. And finally, and actually this was the original title that was kind of a little bit my placeholder title for this talk. In the final part, we'll look at a more recent work where we combined some of the ideas from Bayesian experimental design and active learning, as well as ideas from privacy and specifically sort of cryptographic security to develop a method that sort of allows you to learn collect data for causal inference specifically, right? So the first part will be about causal discovery, and the second part will be about causal inference. Okay, so just a quick recap of what we talked about yesterday. So rather than starting with data and making, all of these downstream tasks, such as predictions, modeling, proving, disproving hypotheses, and so on, in BED land, we actually design the experiments that will give rise to the data, right? And as we discussed, many problems can be formulated as an optimal experimental design problem, such as devising online surveys, things like drug discovery, and things like active learning. So building predictive models in a sample-efficient manner. The way that we did that is by sort of taking an information theoretic approach, right? So we said that the optimal design, Xi, is the one that will give rise to the maximally informative data about this quantity of interest. And this quantity of interest was this parameter set in our Bayesian model, right? So this was the kind of the assumed factorization of our underlying Bayesian model. We have our design, we have our parameters, and together they determine the outcome of the experiment. As we said, the goal was parameter learning, and we do that, using standard Bayesian inference, kind of estimating a posterior from our prior and our likelihood. Okay. Now, to actually quantify what constitutes a maximally informative experiment, we looked at this information gain quantity, right? So this is just the difference between our entropy of our prior and the entropy of our posterior. And to get to a metric that allows us to rank experiments before actually conducting the experiment, we simply took the expectation with respect to the Bayesian marginal distribution of all possible outcomes, right? So this is our expected information gain, which is what is most commonly used in Bayesian experimental design. And again, this kind of goes back to Lindley 70 or 80 years ago now. Right. That was the quick recap. Now we'll move to kind of looking beyond parameter estimation in our model. And just a quick note, right? So the expected information gain really is the most used criterion for designing experiments in the BED framework. But many other alternatives exist. And actually the general recipe for coming up with such criterion was given again by Lindley shortly after he introduced sort of the Bayesian framework for optimal experimental design. So the general recipe is as follows. We're going to start with a utility function, u, which is just a function that maps our parameters, designs, and outcomes to a real number, right? So this function will give you a numerical value for the utility of this design outcome pair, assuming the theta is the true theta that generates the underlying data. Then we're just going to average over all such possible parameters, right? So this is, I'm using the notation of capital U. So this is the utility of the actual design outcome pair on average over all possible parameters that we postulated under our prior. And then we're simply going to average over all possible outcomes as well, right? And this gives us an expected utility of the experiment. Now to bring things back to the EIG, right? So the EIG uses this log density ratio of our posterior to the prior as the small u that we defined. Then the utility itself, taking this average over all possible parameters gives you the KL divergence between these two distributions. Okay, and finally we take an expectation with respect to the outcome y, and that gives us the expected information gain. I see some people taking notes. The slides will be available, so don't feel the need to write things down. Are there any questions so far? Okay. And this sort of general recipe allows us to pick functions that actually are aligned with the goal of whatever we're trying to do. Oftentimes, this is precisely the reason why we refer to this sort of going beyond parameter estimation as goal-oriented Bayesian experimental design. So some papers treat this as specifically goal-oriented BED. And here are a couple of examples, right? So you could look at optimization. So rather than parameter learning, we will want to find the maximum of a black box function, right? So this is the classic sort of Bayesian optimization setting. And here I've given you the expected improvement utility function, something that has been established ages ago. We can perform model discrimination rather than parameter learning. We can pick as a utility, again, it's a KL utility, but basically we are trying to maximize the separation between a model and an alternative model. We can focus on prediction, right? So rather than, if you have a non-explainable, non-sort of mechanistic type physical model that the parameters in your model don't actually have an underlying physical meaning, why would you want to learn about the parameters, right? You will be using this more as a predictive model as opposed to, kind of explanatory parameter learning situation. And, you can aim to maximize the predictive likelihood at some target input, right? So this was done in recent work, and I feel we might be hearing about that work later today, or maybe not. But yeah, the group in Alto had this paper. I think it was ICML last year or NeurIPS last year, right? So all these things sort of follow under the this generalized decision theoretic approach that was proposed. I mean, developed by Lindley quite some time ago. Okay. Oops. Okay. And for the rest of this talk, I will actually focus on designing experiments for causal inference or causal discovery. And in a sense, I mean, it kind of goes beyond parameter learning simply because we're not only interested in learning the parameters in your model, we're also trying to perform what is called structural learning, right? So we're going to have a graph or a structural causal model with a directed acyclic graph that we actually want to uncover, the various edges and the directions of these edges. Okay, so causality 101. Hopefully this is, that's very basic, but I think it's important to make the point. So this chart was taken from a paper in let me just double check. New England Journal of Medicine, right? So this is a very high impact journal, and clearly it was done to actually prove a point that causation and correlation, well, correlation doesn't imply causation. And the paper looked at the, chocolate consumption and a number of Nobel laureates in different countries, okay? And, a meaningful question is asking if we were to set chocolate consumption to 50, right? So this only goes to about 15. So actually nobody has 15 kilograms per year per capita. But if we extrapolate this and set chocolate consumption to 50, what is a sensible prediction for the number of Nobel laureates, right? And to answer this question, you have to make a causal assumption, right? I mean, you can say, I can't answer this question, which is also a valid answer, I guess. But if you were to give a prediction, you kind of have to make a statement. Does chocolate consumption cause increase in Nobel laureates? Does Nobel laureates cause you to consume more chocolate? Or is there something else, right? And indeed, purely from this data, purely from this observation of data, we cannot distinguish between the three cases. Chocolate consumption causing Nobels, Nobels causing chocolate consumption, or actually there existing a third variable that we call a confounder that actually causes both, right? So we know there is a relationship because there is correlation, but we cannot distinguish which of these three cases gave rise to the data, okay, purely from observation of data. What we can, of course, do is actually perform experiments, right? Or rely on some form of domain expertise. Now, relying on domain expertise is easy when you have 2 dimensions, right? And things are simple, right? If we were to ask a totally different question, does gene X cause some form of mutation? Even if you're an expert, it's very hard to tell. So yeah, the 2 sort of things that we will be able to do is impose structure by, giving assumptions, making strong assumptions and relying on domain expertise, or actually performing interventions. And this is where Bayesian experimental design can come in very handy. Are there any questions so far? Okay. Now, how can interventions help? So how can experimentation help? This is a causal DAG, so I made it slightly more complicated. This is this causal directed acyclic graph. And in such a DAG, variables are generated according to a topological order. Namely, each variable will depend only on its parents that are earlier in the graph, right? So for instance, this guy here will be determined by its parents, namely this guy and this guy, okay? And intervening on a variable can reveal this underlying causal structure in two ways. First of all, the dependence with the parents will be broken, right? So if we were to intervene on this node, either changing the distribution or actually setting it to a specific value, the causal parents will no longer be able to influence the distribution of that node. And second of all, setting this distribution to a value or to a narrower, or just changing the distribution of this node will also change the distribution of the children's nodes if there is a causal relationship. Okay. Now, there are very big problems with the field of sort of causal structural learning. And probably the most prominent one is the fact that the space of possible causal graphs grows super exponentially in the number of nodes or the number of variables. So if you have only one node, you have one DAG. If you have two nodes, you have three possible DAGs. By 3, you already have 25 possible DAGs. And for n equals 10, you have a lot. I mean, I don't know how does that compare to the numbers of particles in the universe, but it's probably getting close, right? And this is only n equals 10. So search in this space becomes intractable even for moderate or even small n. And what makes it worse is this is a discrete problem, right? So we cannot really use something like gradients to easily optimize and find meaningful representations, simply because switching on or off one edge and keeping everything else the same can give you a totally different answer. So searching such large discrete spaces is actually very hard. And there's some work showing that learning a causal model is NP hard. So the question is there any hope? And thankfully, the answer is yes, there is, either with assumptions, as we discussed, or with better data, i.e. experimentation or interventions. So kind of a more recent work showed that learning sparse causal models is not NP hard, actually, assuming that the maximum number of parents of any node is bounded by a small constant. In many cases, that might be a reasonable assumption to make. And then you can actually proceed with something that runs, I think, in polynomial time, but it might be. I think it is, but yeah, I will check the reference. And then performing interventions, i.e. performing experiments, can also reduce the complexity considerably. There is quite a lot of work actually showing, depending on what assumptions you're making and how many interventions you're making. The problem of finding the optimal set of interventions, however, still remains. So finding the optimal set of interventions is still very hard. And if you'd like to kind of read a little bit more philosophical, where should the field be going, I can point you to this ICML position paper from last year that causality needs scientific pragmatism. And I think I kind of agree with that take, right? I think we have been, the causality, I mean, I don't think I consider myself part of the causality field, but kind of as an outsider, it seems to me that, progress has been stuck a little bit between the two extremes, right? You want to be scientifically perfect, i.e. you kind of want to use causal models only when the assumptions are provably correct, and they never are, right? And it's a very easy rebuttal to say, oh, but your causal assumptions don't hold, so like, why are you giving me this model? And on the other hand, we have kind of the deep learning people that just don't care about anything as long as it's predicting, it's so fair. And in reality, we probably want to trade these things off in order to kind of get to something that is more trustworthy and more behaves better once you kind of go outside of your domain or outside of distribution. Okay. And with that, I will move to the kind of this slightly old by now work, differentiable multi-target causal Bayesian experimental design. Let me just check, are there any questions or comments? So we are doing causal discovery here, okay? I am not gonna go through any sort of methods that actually describe how you're doing the causal discovery. The focus here will be on the kind of designing the experiments, but there is a good survey, do you like dogs, from a few years ago. So the goal in this work will be to find the most informative interventions so that we identify the underlying structural causal model as quickly as with as few samples or as few interventions as possible. We're making the standard causality assumptions. And this is sort of the overall setup, right? So our hypothesis space will be parameterized by parameters of these functional causal mechanisms, right? And the actual causal graph. So we're denoting this by theta, and you can think of theta as the same theta that we had before, right? But now it actually contains parameters and graphs. We will be performing interventions, right? So to perform an intervention, we actually need two things. Number one will be to choose which node to intervene on, right? So in this example here, we're intervening on the yellow one, okay? And then we also need to decide what value to set the node to, right? So our design will be this sort of tuple of the node and the value with which we're intervening. Okay, and kind of the TLDR really is we're doing almost standard Bayesian experimental design with kind of a slightly expanded expected information gain criterion, right? So as I said, thetas here are parameters and graphs, and we're simply estimating and maximizing the expected information gain in this predictive form, right? So the log density ratio between our outcomes, given parameters, graph, and designs divided by the marginal distribution of these things. So we are performing parameter learning together with structural learning. Is there a question? Okay. Yeah, no worries. Okay. So this is our objective. We are using nested Monte Carlo and importance weighted nested Monte Carlo to kind of avoid recomputing posterior errors every time. All of the details are in the paper. I'm probably not going to go through them here. But there is one key problem that we didn't discuss yesterday. Right, so yesterday we had everything continuous, kind of, right, and we are just running stochastic gradient schemes to find the designs. Now here we have to make a discrete choice, right? So choosing the intervention targets will involve, well, you know, you're picking out of a discrete set of points. And the solution we are applying here is to use actually continuous relaxation so that we can still use stochastic gradients to actually learn an intervention policy, right? So we're using something called the Gumbel softmax or the relaxed Bernoulli, depending on whether we're doing single target or multi-target. And we also have another case where where you're allowed to specify the exact number of targets to intervene on, right? And here is a kind of a quick picture of how the procedure works. So this is our intervention policy that we're trained with stochastic gradients. This intervention policy, and we have 1, 2, 3, 4, 5, 6 nodes in our graph. The intervention policy will give us a vector with zeros and ones, indicating which node we're intervening on, right? So it doesn't have to be one hot, because we can do multi-target as well, so we can have more than one. And of those nodes that we're intervening on, we will be given, the policy will also give us the value with which to intervene. Okay, this is kind of the high level description of what this sort of allows us to do. And here is kind of an empirical result. There are more results in the paper. I've just focused on this one because it's a little bit more, I guess, real world. So this is results on this E. coli gene interaction network. We have 10 nodes, and there is this dream. Yeah, it comes from this dream simulator. So everything is semi-synthetic, right? I mean, there is, you kind of need to know ground truths, or otherwise there is no way really to easily assess quality. We are doing, so this is our approach, the differentiable causal BED. This is from a paper a few years back, from ETH. This is a random policy, so random interventions with fixed interventional value. And this is random, we're intervening on a random node with a random value. And I mean, we can kind of see that this approach performs a bit better than baselines, especially once you get enough interventions. And once you allow for many interventions, actually some of these random procedures work as well as this BED approach. These are just different metrics. So expected structural Hamming distance, F1 score, and max mean discrepancy. Okay, I'm just going to pause for a second and see if there are, many questions. Okay, we'll start here, and then Michael, and then, yeah.
Sorry, could you just clarify what your nodes are here? Because in this example, you've got actual genes interacting, but I think you were sort of talking about causal inference before, so you would...
No, this is discovery. This is causal discovery. The next part will be on the inference.
Okay, so this is sort of factors on a gene, not genes themselves interacting. I'm just having trouble. What does it mean when you go from 0 to 1 in your treatment?
So I will need to get back to you for the specifics. So there was someone else who kind of knows more about the biology / gene.
Not necessarily, but sort of on the previous slide, you had a load of zeros and ones. So you're changing a 0 to a 1.
Yes.
On that. So what does that actually mean in this situation?
So it means, let me come back to this one. Maybe this one is slightly easier. It means that we are changing, we are setting the value of this node to a specific value.
And what is that node?
Well, it depends on the example.
Okay.
Right.
So in the biological example, what would it be, for example?
So I think I'll have to get back to you. So there is this whole procedure of knocking out genes that I'm just not a super expert on, but I think it's best if we discuss that offline. But yeah.
Okay, I work on the same.
Oh, okay, okay.
I can just so it's gene expression, okay. and effectively you have possibility to knock out a gene, meaning that does not anymore have any expression, so you can imagine that the expression level is set to 0. Okay? And I assume that you have other intervention. You can also, in practice, you can also reduce the level of gene expression, or you can enhance it.
Right.
And then you can measure the influence.
Thank you. Yeah, so I just don't know how the knockout mechanism quite works, so thank you. Does that make sense? Yeah, kind of. Yes.
On the results slide.
Yeah.
Yeah. I was, I guess, surprised by the efficiency of the random policy.
Yeah.
In particular, that it's actually later substantially or clearly better than the previous method.
Yeah.
What is your understanding of that? Maybe from either why is random here so good, and perhaps why does it beat the, not yours, but the previous work?
Yeah.
Maybe did the authors there discuss why some high performance drops or flattens out as they gather more samples?
Okay, so on the final one, performance drops or flattens as you gather more samples. I don't see it anywhere kind of dropping, right? I mean, it's still within error bounds.
I mean, I guess I was more looking at the yellow line.
Oh,
because
okay.
it flattens out after 5 intervention samples.
Yeah. So I mean, honestly, random designs work surprisingly, or maybe not so surprisingly, really well, because I mean, you're not making any assumptions, right? And you're not running the risk of getting stuck in an optimization hell that you can't escape from. And I mean, to me, it's actually not surprising that random does really well. I don't know. Yeah,
it's a bit like in reinforcement learning, where the random bit is also inserted just to have a little bit more exploration.
Yeah.
Is it similar, you think?
Very likely. Yeah. So. There was there and then. Yeah. Yes.
Yeah. So yeah, it's related. Can you comment on the metrics you are using? So you are just comparing the accuracy of the graph. Or?
So this is a metric called structural Hamming distance. So we are comparing to the true underlying graph, right? So I guess this could be the closest to an accuracy that we are, comparing what we've learned or what we've estimated to what the true underlying thing is. I guess, like, to me, that makes most sense as a metric.
So the result you get.
Sorry, I can't hear. Sorry, I can't hear. Yeah. Yes.
Yeah. I was wondering if the results could depend on how you measure the distance between the graphs.
Sure. Yeah. I mean, yeah. There isn't. I guess there isn't a one way to measure.
So that's what the first graph, but the other ones, the first plot, the other ones also.
I mean, again, this sort of gives you an overall idea of, like, if you were to measure quality of your estimate, if you're measuring quality of the learned graph in different ways, you know, how are these different things performing? And overall, you kind of see, I mean, the fact that they're kind of very consistent tells you something, right? I mean, they're not all exactly the same, but the fact that this method does particularly well between 5 and 10 interventions, and then actually everything does pretty much exactly the same after, well, except on this one. But the two random policies actually catching up after 10 or so interventions, that kind of gives you kind of a consistent message, I guess, in terms of, how things are performing. And I think there was one more.
I was just thinking maybe the fact that they look so similar, there's not that much of an advantage
To not having an advantage to being
strategic about interventions.
I think, I mean, that's one. It is a little bit hard to tell, right? Because we don't know whether there is an optimization problem that has happened, whether our nested Monte Carlo estimators are giving us, sensible estimates, whether actually computing posteriors over graphs is in itself a super unpleasant problem, let's put it that way. And so I think there are many things that kind of might be working against us here, under the assumption that we can solve all of them perfectly. I would expect there to be a better performance gap. But given the tools that we have, I guess you're right to say there isn't, I guess, sufficient evidence to claim that one method is much better than random.
And the space is so large.
Yeah.
That it's kind of actually exclude.
Yeah. So I mean, that's d equals 10 nodes, and I showed you how many DAGs there are. I mean, generally speaking, when we are, and again, I would refer you to the review of methods for active for causal discovery. But oftentimes we are regularizing the graphs towards sparse graphs as well, because otherwise, I mean, there is no hope really. Okay, great. Thank you so much for all the questions. Okay, so now we will move to this secure active dataset acquisition. This will be causal inference as opposed to causal discovery. So here we will be assuming the graph was given. And actually the title of this paper is a bit long. It's called Is Merging Worth It? Securely Evaluating Information Gain for Causal Dataset Acquisition. And this was this year AI Stats. So let me just go through this title. So merging, imagine we're in this setup where a pharma company has performed a clinical trial in one hospital, let's call it Hospital A, and now it wants to run a second trial in one of K hospitals, okay? And it wants to evaluate which hospital would be, the data from which hospital would be most beneficial for the purposes of determining whether the drug is successful or not, okay? So when we're talking about data set acquisition, here we will be again information theoretic. So we'll be picking the one that maximizes the expected information gain. Causal, well, I guess I just said that. So we will be improving estimates of treatment effects specifically. And securely, we actually want to guarantee that no information gets leaked. And this is quite important in cases like sharing data between hospitals, because of obviously privacy concern for patient data. Okay, and this is the overview of the method. So we're going to have what we call a host site. Oops, sorry. The host will define a probabilistic model with some prior over its parameters, and it will compute a posterior with that data that it has, right? So this is the pharma company that has already run a clinical trial once, and it has a posterior, okay? Then we're going to have these K candidate sites, and the model class will be shared among the sites, these candidates, okay? And what we want to do is for the host site to securely communicate the information about this posterior to the candidates. The candidates should be able to compute the expected information gain at each of these points, and then return the expected information gain securely as well to the hospital, to the host site, or the pharma company. Is that okay, more or less? Yeah. Okay, so here we're actually going to assume the causal graph. We're going to have covariates X and treatment allocation T, and together these will determine the binary treatment outcome, so zeros or ones. The treatment allocation schemes and the covariate distribution can differ from hospital to hospital, from this candidate site to another candidate site, but this outcome distribution will be fixed. Okay, and this is an assumption that we're making. So as before, we're going to have the standard data generating process. We're going to sample from our prior, and then we're going to sample the outcome conditional on the parameters and the covariates in the treatment allocations. The goal will be to estimate the conditional average treatment effect, or the CATE. And under standard assumptions, the CATE is identifiable, and it will be given by this difference in expectations, right? So this is the expectation of the outcome given treatment is 1 minus the expectation of the outcome given that the treatment is 0. So this is kind of the potential outcome framework. We are going to assume, actually what I had in the previous slide is, what I said in the previous slide is wrong. I said the outcome is binary, but I was supposed to say that the treatment is binary, 0 or 1, and the outcome is actually continuous. Apologies. So the outcome will be continuous, and we're assuming that it's actually normal, right? So the likelihood, the mean of the normal distribution will be given by the mean, and we're going to have some fixed sigma squared, right? So we're not going to model the variance. And the estimate of the CATE will be therefore in this form, right? So it is the difference between the mean given treatment 1 and the mean given treatment 0. Now another assumption that we're making is the type of probabilistic model that we are working with. And specifically, we will be using models that sort of decompose parameters into those that directly affect the treatment effect and other nuisance parameters. So we have this splitting of the overall parameter space into theta non-causal and theta causal. Okay, and one example of this is Bayesian causal forests, right? I guess if you've worked in causality, this is a very popular model, which is given by this expression here, right? So we have the parameter that affects, the parameter that doesn't affect the causal, the treatment effect, and the ones that do. The metrics of interest will be 2 of them, right? So we're going to look at the expected information gain about the underlying causal parameters only, meaning that we'll be integrating out the nuisance parameters. And we're going to look at this PEHE, precision in estimation of heterogeneous effects, which is sort of equivalent to the mean squared error between the true CATE and the estimated CATE. Okay. Now, how are we going to guarantee the privacy? This is kind of a very high-level overview of the methods that exist. The first one that you've probably heard of is differential privacy. Those who have heard of differential privacy? Okay, great, yeah. So the high-level idea is to noise the input data, right? You're noising the input data, and therefore you cannot attribute any, you cannot sort of backfill or like infer any of the individual patients' data points. In a sense, this gives you a privacy accuracy trade-off, right? The more noise you add, the better your privacy, but also you will be destroying a lot of the signal in your data. Then you have something called fully homomorphic encryption. where the high-level idea is to encrypt your data and then actually perform computation on the encrypted data. This is great. Like if that happens one day, that would be amazing. But currently, it's really not feasible beyond very simple cases. And finally, we have something multi-party computation, which is what we're using here. The high-level idea is that each participant will be sharing portions of their data, and there will be the computation will be performed collectively. We'll be following. I mean, there is an underlying protocol called secret sharing protocol, which basically guarantees the cryptographic security and allows us to compute arbitrary functions, right, such as the EIG, without actually revealing any of the data involved in the calculation. So the advantage of this is that we can keep all of the computations secure, cryptographically secure, and only add noise at the very end, right? So we can only add noise to the final EIG when we are communicating it to the host, as opposed to adding noise in the underlying data and then sort of removing a lot of the signal in the data. Who here knows what MPC is? Multi-party computation. Anyone? Okay, I'll very quickly go through it. It's very simple, actually. I mean, it's very simple for computing a mean. So here we have three people, Alice, Bob, and Charlie, that want to communicate, that want to figure out what their average salary is. Okay, and so Alice has a salary of 200K, Bob 180, and Charlie 210. And what they're going to do, each of them is going to split their salary into 3 chunks. Totally arbitrary, right? So you can do, so Alice is doing 50, 120, and 30, so that adds up to 200. And then Bob and Charlie are doing the same, right? So minus 80, 240, and you can have negative numbers, that's all fine. And you can, each of them, so each of them is splitting their number and then communicating. So Alice is communicating 120 to Bob and 30 to Charlie. And then each person has 3 of those numbers, right? And they can actually communicate the sum and then take the average of the sum, right? And nobody can actually reverse engineer what the salaries of the other person is, right? So this is literally relying on the fact that if you sum like this and then average, or you sum like this and then average, you get the same thing. Okay. And the raw data cannot be recovered. There are lots of protocols that basically tell you how to do, I think, pretty much any, apply pretty much any function. So for multiplication, there's something called beaver triplets. Things become a little bit more complicated. There is some randomness that needs to be added. For logarithms, there is something called householder iterations. For the log determinants, actually, this is something that we had to implement for the log determinant of the normal likelihood, because we are working with these expected information games with normal likelihoods, which involve taking log bits of your covariance matrices. We are relying on the Cholesky LDL decomposition to do that, right? And then there is a list of various other computations that you can do. There are a couple of assumptions that actually underlie this cryptographic security. Something called the semi-honest settings. So all parties follow the protocol correctly, right? So if they don't, if they lie about how they're splitting things, right? That's not going to work. So people have to be honest. And yeah, basically you cannot learn anything that can be inferred from the final answer. So if it's only 2 people calculating their average salary, then obviously you can figure out what the other person's salary is, but with 3 you can't. Okay, I'm running a little bit short on time, so let me just very briefly describe this synthetic experiment. it's actually a bit complicated. So, okay, we have a simple linear model setting, and we only have k equals 2 sites. And what we'll be doing is have 2 data generating processes for each of the k sites, for each of the 2 sites. One site we're going to have what we call a complementary data set, and the other one will be twin. So the complementary data set will be exactly the missing part that will, together with the host data set, will basically recreate a randomized control trial. So this will be the ideal merge, okay? And the twin will basically contain the same distribution as the original host. And what we'll be looking at is the ratio of data set sizes on the x-axis, and on the y-axis we'll be looking at the difference between the EIGs, and on the secondary axis we have this PHE metric that I described earlier, right? This mean squared error between k's. And what we are seeing, and again, because everything is quite simple, we can compute things in closed form as well, and make sure that we're not like too far away once we use MCMC to calculate posteriors. What we see is kind of this slightly different behavior in the 3 regions. In the first region, both the EIG objective and the EIG and the PHE favor the complementary data set, right? So this you want to be positive, and this you want to be positive. So the complementary data set is favored in this first region. In the second region, the EIG that targets parameters in the entire model as opposed to just the causal parameters actually incorrectly switches to the twin data set. And then in the third region, both methods correctly select the twin data set, simply because you have way more data in the twin data set as opposed to in the complementary data set, right? So once you reach a certain level of data, you know, size actually matters more than, and again, like you are kind of covering most of the RCT anyway. Okay, these are some other experiments, not particularly nice to look at big tables, but you know, there we are. And just very quickly, finally, this is on the privacy guarantee, right? So we compared to the standard differential privacy protocol for linear regression, and actually, as I said, the rank correlation, if you were to noise the inputs, basically goes down to 0, right? So you're merging with something that actually has no correlation with what is the best thing that you can do. And this is with our MPC protocol, where correlation is still very high. Okay. I'll stop here. This is just a very brief summary of what I've talked about. So yeah, happy to take any more questions.
Thank you very much. So, coming back to the interventions on the network, and this idea that sometimes was disappointing because some clever strategy,
yes,
for example, design doesn't work so well, compared to random design. So, don't you think that it's closely linked to the density of the network in terms of interaction?
In what way? So if you have a very dense network, and we are imposing some sparsity
if the ground truth is very sparse,
right?
In fact, and you have only 10 nodes, in fact, I mean, if you ask, if you intervene with a knockout times time,
Right.
It's probably, it's the case that if you have very sparse
Right.
interaction, you know everything.
Right.
About-
If you right. So
Yeah.
with 10, you actually are able to.
Yeah, I mean it's
if
very,
it's
very
sparse.
sparse.
Yeah.
If it's
Yeah.
completely dense, and then
Yeah.
random strategy has no effect because it does not earn.
Right. Yeah. I mean, possibly. Yeah. I don't. I mean, we didn't look at, sparsity versus performance. I think that can be a nice thing to look at. Yes. So I guess the conjecture or the claim is that the sparser your graph, the better random does, simply because you can uncover the graph with very few interventions,
Yeah,
right?
with the kind of interaction
Yeah,
we
yeah.
have.
Possibly. Actually, that's a very good point. Yeah. Thank you. Yeah.
Yeah, any question on the... So yeah, you had many questions through
Yeah.
the talk, so I will relate that for the coffee break. Thank you very much.
Thank you.